In the last class, we took the first steps in formulating a strategy for analyzing thermodynamic systems, and that started by saying that we make a sketch of the system as realistically representative of the real device. Then we define the system boundary, and that tells us what is in it and what is not in it. We then look at and say, is there heat or work transfer across the system, and that is the definition of heat and work. Then we ask, is there any mass crossing the system boundary, is going in or going out from the system? And then we define these special types of systems, isolated, closed, and open, and said that if the closed system, the equations will be formulated in the control mass approach, the CN, and in the open system, we look at the systems and the equations in the control volume approach, the CV approach. So we will now pick up on this and say that we then define what is a state. This is our next major concept that is coming up now. And to define the state, we said there is a state of a system always. And what we mean by state is that we have a set of properties, and we just call it P1, P2, P3, and so on. And we say that it is these set of properties that define the state of the system. What we are implicitly saying is that these are not just properties of the system, but actually properties of the substance or the material which is the system. So we are always now beginning to say that whenever we say properties of a system, we actually mean properties of the substance. We are not putting any restrictions on this at all as to what is the substance. Is it liquid, or whether it's a mixture, is it pure, what pressure is it? Absolutely no restrictions. So let's first define what is property. So this is a characterization, numerical characterization, value based. A numerical characteristic of the substance. That means if we define that there is something, so can I put a number on it? And if the answer to that is yes, then you say, okay, so I call this a property and I'll put this number on it. So let's take an example and say, well, how do I characterize a person? Person A. That could be a human being or a living creature, a dog or a cat or anyone. Say it's a human being. So, well, what are the properties by which I can define the state of this person? And say, well, okay, you can say that this person is 1.2 meters in height, weighs 45 kg, has a blood pressure of 120 by 90, and various other things. And these days, if you go to any of these laboratories, they will tell you that your hemoglobin is this much, your RBC is this much, and various types of cholesterols are this much. And so many numbers will come out. And one can say that all these, in some way, each one of them is a property of a person, and all of these together are defining the state of this person. What it's also telling us is that how many properties can I have? And the answer is that if you look up the way materials are characterized, besides the microstructure, you will come across about 40 odd properties of a substance. And since we did not put any restriction on what that property is, anything that qualifies this thing that you can put a numerical value on the characteristic of the material is a property. So this gives a very large number of properties, some of which are useful in this course, some of which are not. But the thing that one can look up is to see a package called Cambridge Engineering Selector, where few lakh materials have been listed and their properties have been given, and like this many of these properties. And this is a device from which we can say that I want a material with these properties, which is a candidate material, and the software package will tell you, okay, can pick up this material. So this is a very, very important thing that is happening in today's age and time. Every day, many new materials are being discovered, and essentially, this is the crux of technological innovation and technological change in our time. We talked yesterday about solar photovoltaic cells, the material of the cells, the various things we put in it, that is coming from it. We talked about gas turbines, aero engines. One of the big things that is driving aero engine technology, and we saw how much it has changed, is properties and the materials of substances used to manufacture the engine. And like this, practically there is nothing where today some innovation here is not driving what is required, but what is required is dictated by thermodynamics, and which is why we are learning this subject. So we come back and say, well, what are the properties that are of interest to us in this thermodynamics? And we say that, look, if there is a substance, and we just take, say, an elemental volume of that substance, then in this, there would be lots of atoms and molecules in this in anything. So we're not going to worry about how many atoms are there or how many molecules are there and what each one of them does. What we will, if that is to be done and we want to characterize it, we have to go to the microscopic approach, where we start looking at each and every atom or each and every molecule in this, and then say, what is the property from there? And this is what we do in statistical thermodynamics. In this course, which is what is classical thermodynamics, we do not worry about what each and every molecule is doing, or maybe even what 10 molecules are doing, but we say that this is a big enough volume so that there are a very large number of molecules, and so if I take similar thing from anywhere else in the system, they will all have on an average the same behavior or the same properties. This is what we call the macroscopic approach, and implicitly we are assuming that we have a continuum. That means the size of this on an edge is such that it produces a volume in which there are very, very large number of the atoms or the molecules, and that statistically we can characterize their behavior by certain numbers. And that is what we characterize. This is the continuum approach. So we are saying that the individual molecules or atoms are not the issue. If this dimension were of the order of the intermolecular spacing, here we call this distance d. If d is of the same order of the intermolecular spacing, then we end up in the microscopic approach. We do not have a continuum, and everything we learn cannot be applied. So if you are looking at, in today's age and time, nanotechnology and microtubes and nanotubes, where the dimension is of the order of this, then this approach is not suitable. We have to go back over here and redo everything in a very different way, and the answers are quite different from what you get from here. That's a major thing these days. So there are a lot of people working on it, a lot of advances taking place there, and this is the crux of that. What is micro and nanotechnology? In our case, we say that D is of the order of hundreds or maybe thousands of the intermolecular space, or even more. So the individual atoms and molecules do not matter. We take all of them together and assign certain properties to them. In the cases of gases, we have the well-known kinetic theory of gases. It's a very, very powerful tool to look at many aspects of what we see in the real world, including things like chemical reactions. Okay, so what we are going to do is, we are studying that part of thermodynamics, which we call classical thermodynamics. We go by the macroscopic approach. We assume that the substances are a continuum, and now we begin to say, what are the properties that I can assign in a macroscopic approach? In the macroscopic approach, the property would be the velocity, say, of each and every atom, the temperature of each and every atom or molecule. And you've got billions and trillions of these. How do I put it together? Well, you take statistics, do some averages, and then tell, well, this is the typical, most probable answer for this. We don't go by probability, we go by fixed things, what is happening here. But before I go there, just to tell you that, well, just because we are doing it doesn't mean this is not very important or exciting. This is in its own right a very exciting field of knowledge or physics, and a lot of things that we do here can actually be explained from here, and in a very, very rigorous and a very elegant way. We won't go into the details of it later on, but when we look at, say, entropy, it is much more easier to comprehend from this approach what entropy is than trying to see from this approach. Okay, so let's now go back and see what are the properties that we have. And we can say that we can classify properties in two ways. One is what is called an extensive property, and the other intensive. Very simply, extensive property is some number of the system or the characteristic of the system that depends on the size or the extent of the system. And intensive is something that does not depend on the size or the extent of the system. Okay, so what does that mean? We go back and say that here is my system. Okay, here is, say, a room, and in this we make our system, which we say is everything in the air in this room except the walls of the room. So the surface, the system boundary is right next to the surface, but not including the surface. So that's the first thing we did. We said, define the system. And we said what is included, what is not included. And next, we say, well, what can I say about this system? So I can tell you what the volume is, what is the mass, and one can add on things. Later on, you can say what is the energy of this, things like that. So it means that if this is the system, I get a certain volume. If I take a portion of this, I get some other volume. So it depends on the size of the system that we are looking at. And if these systems that we make, subsystems, which are completely independent of one another, then adding that property for those systems will give you the property for the system. So for instance, we chop it up into 4 parts. Then the volume of this plus volume of this plus volume of this plus volume of this is the volume of the system. So it has what we can say an additive property. And the same can be said about the mass. Remember, mass is quantity of matter. We are not using the word weight. That is wrong because that's the force. So this is an extensive property. And many an analysis is much easier to do. We say, look, I have one system today which has got a certain volume. Tomorrow I'm going to make another system which is much bigger than this. How can I take the result of the smaller one to the bigger one? And an extensive analysis doesn't help us to do that. And that's the main reason we then go to the intensive property and say, look, can I make a property which is independent of the size of the system that I take? So I take a little elemental volume there, or I can call it that at this point in the system, if I can put some properties and if it is same everywhere, it is an intensive property. It does not depend how big this whole system was. And examples of that is pressure, temperature, and then you can say, okay, thermal conductivity, electrical conductivity, specific heat, and we use a large number of properties which are extensive, but we make them intensive. So we say that any property per unit mass or per unit mole is an intensive property. So if we take volume per unit mass, that is meter cube per kg, this becomes an intensive property, and this we call, in all these cases, specific property. So meter cube per kg will qualify as specific volume. And this is nothing but the inverse of density. We are much more familiar with density because that's what we have learned from school days. But from now on in thermodynamics, we always deal with specific volume. The two are just reciprocal of one another. So this is mass per unit, volume per unit mass, that is the specific volume. Or you can say, what is the volume per mole? Again, that is molar specific volume. And that helps us in analyzing things like how much nitrous oxide is formed in the combustion process in a diesel engine, for example. So this is an important thing we have done. We have converted an extensive property to an intensive property. Okay, so now we have said that if I have to go back and say, what is the state of the system? That is where we started from. We'll now say that, well, I can specify the state, thermodynamic state, and now that's what we will worry about. We'll drop the word thermodynamic. We imply it implicitly that we are looking at thermodynamic state. The thermodynamic state is defined by a set of these properties, thermodynamic properties, and this we will be again calling P1, P2, and so on. And the next question will come, how many properties do I need to specify? What we are saying is that if I have to completely and define the state of a system, then how many properties do I need to specify? We will come back to this question when we come back in the third module on properties. For now, we will just say that irrespective of what the system was in its thermodynamic part, a limited set of, we can specify a lot of properties, but the subset of that will uniquely specify the state of the system. So what we are saying is, that the system material which is there, so the state, and we are not talking about property, means property of the substance. We first say, well, I want the property of the system. The first question is, what is the substance in the system? And then we start getting its properties. So the properties of the substance. This substance could be just one type of a molecule, which is what we will call a pure substance. So only one type of an atom or a molecule. And it doesn't matter whether this was solid or a liquid or a vapor, or it was a mixture of these two, or a mixture of these two, or a mixture of these two, or a mixture of all three. It is a pure substance. So these are what we call as the phases of a pure substance, and that is one arm of this. The second thing is, the substance could be a mixture of different pure substances. For example, when you say air, technically this is two pure substances, O2 plus N2, and every time if you want to look at O2 plus N2, analysis becomes a bit complex. So in this course we'll say, okay, can I say that this is one pure substance and approximate it somewhere here? So in some problems this is okay, but if you want to understand how much NOx formation takes place, how much emissions take place, we have to think of these two. Or it could be two completely different substances. For example, in an oxyacetylene flame, you have two chemicals, different molecules coming in, and that's what is going. There could be even more of this. And we can say that if air is treated as sort of a pure substance, plus water in it in any form, this becomes a mixture. And this water, we are not worrying what form it is. It could be a vapor, it could be small droplets that give us a mist, or as this is the season, it will give you rain, drops, liquid water. So here you have mixtures of substances in any phases. Life becomes very complicated here. We will not worry too much about this part. In this course, we will cover only this, knowing that the thermodynamics of this can also be understood, but it is a matter of an advanced course in thermodynamics. So we come to the pure substance and say that there is only one atom and one molecule, and we say that I have to define certain properties, and that's what these will be. So we'll worry about pressure, temperature, specific volume. These are the thermodynamic properties. Then there are transport properties. This also includes specific heat, C, Cp, whatever it was, and remember this is units are kilojoules per kg per K. So again, this was specific volume, this is specific heat. The word specific is now coming in here. Transport properties include viscosity, kinematic viscosity, things like that. So we do not need this in this particular course. In fluid mechanics or in a more advanced course, we would worry about this. We would be quite happy with this one. Okay, so what we have done now, we said that we have a system. We say what is its state, and we define the state by first telling what is the substance. Hopefully it is one phase, maybe two phases, three phases, doesn't matter, we specify that also. So to completely specify the state, what we need to specify is, one, what is the substance? What are the phases that exist? And then some properties of the substance. That is a complete definition of the state. What we have implicitly assumed in defining some of these things here, say in this picture for example, when we said that here, 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 at any point, we say that we measure the pressure and say, well, what is the pressure? And if it is same everywhere, we are putting it and we are calling it pressure of the system as an intensive property. what we implicitly assume is a very important concept, is that if we want to define the state of a system, this system has to be in thermodynamic equilibrium. This is a very, very important concept, and very simply, let's first define it, and then we'll go back and see what its implications are. If you take a system, I'm drawing a rectangle, but absolutely no necessity that it should be a rectangle. You can make any shape, as long as it includes the system that we want. And if we say that in this system, at any point that I take, if the pressure at every point is the same, then the system is in mechanical equilibrium. Now we take this same thing and say if I measure at any number of points anywhere in the system, and if temperature everywhere is the same, then the system is in thermal equilibrium. So here T is same everywhere. Here it was the pressure. So all of this then comes up here. And we get a third one. And if we say that everywhere here the chemical composition is the same, then the system is in chemical equilibrium. So we have concentration of different species. Species is nothing but different types of molecules. And then this whole thing follows. And if all these three types of conditions are satisfied, then the system is in thermodynamic equilibrium. So we say, well, what are the characteristics of a system in thermodynamic equilibrium? We can say one, if the temperature, pressure and chemical composition at any point in the system is same, then the system is in thermodynamic equilibrium. Okay, so the second argument that one can say, and put a definition on it, is that if I take a system and then for that instant we isolate it, and I say that this is the system, sorry, this is the system boundary, and I have now isolated this. Isolate means there is no interaction with the surroundings. The system may have been having heat transfer with the surroundings, and if we want to see whether the system is in thermodynamic equilibrium, we say, okay, at this instant, I just cut off the system from the surroundings, and then I wait and see, do properties in the system change? So if you isolate the system, and if properties at any point, so any property at any location, if it changes with time, then the system is not in equilibrium. If at any location the property does not change with time, then the system is in equilibrium. So this issue of time that has now come in, it tells us now that when we talk of equilibrium of a system, we are always first going to make the system and say that at a particular instant of time only we can think of whether the system is in equilibrium or not. So at one instant of time, it is possible the system is not in thermodynamic equilibrium. At another instant of time, it is in thermodynamic equilibrium. So an example of that would be, let's say, if this were a room, and these days we have problem with mosquitoes, so we put our mosquito repellent thing into the plug, and this keeps giving out vapors of various chemicals which are mosquito repellents. And we say that if I take a snapshot at this point of time, is this system, is the air in the room in equilibrium? The answer is, well, the composition here is different from the composition here, so the room air is not in thermodynamic equilibrium. But if we stop putting this out and wait for a long time, then all these molecules will then completely diffuse into the room, and at any point the concentration of this repellent will become constant. Then we say that this room air is in thermodynamic equilibrium, assuming that there is no temperature or pressure changes. What it also means is that the pressure and temperature are same everywhere, then these properties do not change in any direction. All these are identically zero. Then we say the system is in equilibrium. And once we have said that the system is in equilibrium, then we can start assigning properties to it. So whether it was extensive property or intensive property that we saw, all those properties can be topped off only for a system which is in equilibrium. Okay, now let's look at some real cases and say, well, how good are these in terms of classifying this as being in equilibrium or not in equilibrium? Okay, we take say a piece of metal, and we say these surfaces, 4 surfaces are insulated. This surface is heated, the backside is cooled. So we are establishing a system like this, where this side there is heat transfer to the system, this is the system, there is heat transfer out of the system, and the system boundary includes all the metal that is here. If this is thick, and of say a material like stainless steel, then a temperature here, if it is say about 90 degrees C, and the other side you maintain say 30 degrees C, then there are temperature gradients in this, and so this material is not in thermal equilibrium, and so the idea that it is in thermodynamic equilibrium does not arise. One of the issues that arises if this is a solid is that for solids, pressure is not defined. So talking about the pressure of a solid really doesn't make sense. We don't, at the most one can say that what is the pressure on the surface of the solid, but not what is the pressure inside the solid. So we won't talk about that. So this is not in thermodynamic equilibrium. But if this thickness were very, very less, it was like a foil, stainless steel foil, 100 microns thickness or 50 micrometers in thickness, and we say now I'm employing temperature difference of 90 and 30 across it, can I approximate this as being in thermodynamic equilibrium? So then you can say that, look, well, internally the gradients are still there, but okay, you might do it. I said, okay, forget if this was not stainless steel, it was a silver foil, then you say, yeah, okay, temperature gradients here are still going to be there. I cannot strictly say that in thermodynamic equilibrium. But if these temperature differences are say relatively modest, say a temperature difference of a couple of degrees Celsius, depending on the application, then we can say, okay, the temperature difference across this is very small. I can say that it is almost at the same temperature, and I can say this is in a sort of thermal equilibrium, though not strictly thermal equilibrium, and this we say is an example of quasi-equilibrium. Quasi means that the real system is not in equilibrium, but we are making certain assumptions and saying that, okay, that it is approximately like this, and so I can consider it to be in equilibrium, and if the temperature difference was that small, I can say, well, the average of the temperature of these two is the temperature of the system, and that is my system property. So we needed this to assign a property to a system. If we did not assume this, if this was the case, and somebody says, what is the temperature of this material? We can't give an answer. There is no answer. So that's with temperature. Another example is from something that will keep coming back again and again in this course. There is a cylinder piston arrangement. And inside this, there is a gas. Let's for the moment assume that this is an ideal gas. And we say, engine, this is a part of a diesel engine or a petrol engine or an air compressor. And we say, no, this thing is moving back and forth at a certain speed. Can I assume that at any instant, the gas inside this is in mechanical equilibrium? That's the question. And for that, we do the same thing. First, define the system boundary and say, look, this is the system boundary, which runs along the walls of the cylinder, include all the molecules inside it, but excludes the wall. It excludes the piston. If somebody made a boundary like this, we cannot even discuss the system. And so, very precisely drawing the system boundary and writing what's in it and what's not in it is very, very important. So that's what we've done. And we then go back and say that this piston is moving down maybe at the speed of 10 meters per second. And we say, well, is the pressure the same everywhere here? And the way we'll answer this question is to go back to what you would have learned in school physics, and so that if the piston were to move very slightly, say from here, it moves there and stops, then what it has done is that the molecules just next to it for a short distance are compressed slightly, and then because there is a difference in the pressure, this front keeps going out, the pressure behind it keeps decreasing, and gradually the wave comes here, and hopefully the pressure everywhere in the cylinder has become the same. Otherwise the wave will come up to here, get reflected, go back, and in a few reflections the pressure everywhere will become same. The speed with which this wave travels is the local speed of sound. And that is the case with not just gases, but also with liquids and solids. It's the same formula that comes from physics. In air, I'd say about ambient conditions, it depends only on the temperature, not so much on the pressure. At ambient conditions, the speed of the velocity, the speed of sound is of the order of 330 meters per second. Which means that as the piston moved, at a much faster rate, this pressure wave went through and equalized the pressure. So by this still only at 10 meters per second, the equalization takes place at 330 meters per second, and so we can assume and say that, look, the equalization takes place much faster than the piston moves. So during this motion, even though this is slightly not in equilibrium, but as long as this velocity is much less than this velocity, I can assume mechanical equilibrium in this, and that's a decent assumption. And the temperature also is equalized. So we can say in all these problems where the piston is moving very slowly compared to the local speed of sound, that this system at any instant of time, and again this is important, the system is in mechanical equilibrium and in thermal equilibrium. And this is very, very important because then it tells us that at any instant of time, if I have an equilibrium, or if not strictly an equilibrium, we can say that this is quasi-equilibrium, which means that at any instant of time, I have quasi-equilibrium. It means I can specify properties of that system. So at every instant of time, we are able to specify the properties of the system. This is very valuable to us. Okay, so I gave examples of chemical equilibrium, mechanical equilibrium, and thermal equilibrium. And real-world systems, in many of the cases, especially when it comes to thermal equilibrium, may not be like that. But we assume that, okay, take a small slice or make some other assumption and say, well, okay, I can assume it to be in thermal equilibrium or not. And then only we can do any calculations related to heat transfer, work transfer, or anything else. So what we have done now is said, well, what is equilibrium, what is quasi-equilibrium, and only thing remaining now is that if any of these three conditions are not satisfied, any of these three, then the system is not in equilibrium. Okay, so either of those not satisfied, not true. This implies the system it's a non-equilibrium system. And what we are learning in this thermodynamics is not applicable. There is a separate branch of thermodynamics which deals purely with non-equilibrium systems, much more complicated. So at the graduate level or the research level, the undergraduate level, we will not worry about it. We'll say, okay, fine. If I want to get closer and closer and do a better and better analysis of the reality, I need to go there. But at this point of time, I'll be quite happy to go to a quasi-equilibrium system and get at least some basic information. Okay, so that's non-equilibrium thermodynamics. Examples of that: supersonic flow, that is a non-equilibrium system, or mixing of two different substances, or very fast chemical reactions. Those are all non-equilibrium systems. So we won't worry about that.